everything you always wanted to know about CLE, GFF, SLE, planar maps.
Well,
level that one.
maybe not. Thank you, Nicolas. So maybe before I start, I'll start with an unusual thing that occurred to me. That usually, I mean, these things are recorded, and there's somebody in that dark room behind that comes out smiling occasionally, but only when something goes wrong. So people, mathematicians probably not, maybe we don't say thank you enough to him. So I hope he's listening and seeing there, and he's making it possible for all the things for people to look online and later. Okay, so I want to continue the lectures from yesterday. So I'm going to, the goal today will be maybe to state, that you understand clearly the actual statement of the results, of some of the main results that we have in the upcoming papers with Scott and Jason, because they sort of build on various other items that we've been working on in last year's and earlier papers, so that's somehow my main goal, is sort of to set up the stage that you have a clear picture of what the actual statements are, where they come from, why they are in some sense natural. And for those of you who listen to the talks on planar maps and Tim's lecture earlier and Grégory's lectures before, or who have read the papers by Boro, Boutier-Guiter, and I mean, all these list of papers have been listed before, you'll recognize very familiar objects and say, okay, that's what the object that are behind the scene when we compute limiting objects in planar maps. But I will not talk, I mean, I'm not doing anything about planar maps here. I'll be working only in the continuum. So the objects we're going to deal with are the Gaussian free field and SLE and its cousins CLE. So what the main players are going to be, so I just want to first recall you some background on CLE. Right, so the goal will be at the end to state clearly, okay, if I have a certain CLE kappa and on top, in a unit disk, and equip the unit disk with an independent quantum surface, there's going to be an independent Gaussian free field that I'm going to use to define an independent quantum surface with a gamma value that is related to the kappa of the CLE. Then, there's a nice decomposition. You divide things in IID or there's a Poisson point process structure, things like that. So, CLE background. So, what is a CLE? I mean, the philosophy is the following. I mean, one way to look at things is to say, well, our goal in probability and statistical physics is to understand the scaling limit of a discrete model, right? So we are interested in the Ising model, 2 dimensions. We have a phase transition. This is nice and safe. That's the way we teach and are taught these things. And then there's a critical point, and at the critical point something special happens. And the Graal is to show that the discrete model converges, discrete model that you have defined concretely on the lattice converges to something which is a continuous structure, right? A random continuous structure. On the other hand, you could say, well, why do we work on this, on that lattice? It's just by convenience, because it's the nicest and most, it's just a way to represent reality. Another approach would be to say, well, you can define directly the continuous structures, right? And say, well, they are, the natural way to model what's going on in the real life, because they are the only, continuous structures that have certain direct axioms that you can, write down without any reference to a, lattice. And then you can say, well, because these continuous structures satisfy these and those axioms, they are the only, possible likely candidates of the discrete scaling limit of discrete models, if these discrete models happen to, converge to a conformal invariant limit. So in some sense, if you think about it, there's a, I mean, when Odette Schramm defined SLE, you know, in 98, I very quickly realized that, yeah, if the scaling limit of critical percolation exists and is conformal invariant, then it has to be SLE6, right? There's no other choice because SLE6 has certain magic properties. You know, it is an SLE plus it has some additional magic properties. And therefore, you know, you could view SLE6 as somehow a natural model for continuous, for percolation itself, not without any reference to a lattice. In a similar way, you could say, you know, the measure on self-avoiding loops, SLE 8/3 self-avoiding loops, is a natural measure on that you can make sense of. So it's a measure on self-avoiding loops in the plane, and it's the unique one that satisfies very simple axiomatic properties, and therefore it is the unique possible, scaling limit of self-avoiding loops uniformly chosen in some sense, at criticality. And that's somehow, this is sort of a general idea. And so CLE are, basically without reference to the discrete lattice model, the only, possible candidates for describing the joint scaling limit of everything that happens on a lattice model. So the way you view it is you have a parameter kappa, so it's going to be important, in what's going to happen later. That here for all this CLE story and most of what I'm going to say here, there's this restriction that kappa has to be between 8/3 and 8. You should think of the limit when kappa is equal to 8/3, the CLE is just empty, there's nothing. And when kappa is equal to 8, it's the space filling, SLE 8 that surrounds it, so one space filling loop. And maybe for the purpose of today, we're going to focus on kappa, between 8/3 and 4. But for most of what I'm going to say in the first, in the recalling things about CLE is going to be, valid also on the other side with some minor differences. So the idea is, suppose it is going to be supposedly the scaling limit of an ON model. That in the unit disk, so it's a random collection of loops that you define in the unit disk, and because I'm in that regime where kappa is smaller or equal to 4, these loops will be self-avoiding, and so simple loops, and they don't touch each other. And also, there's another remark that I want to make, that there are two versions of, which reminisce of many things you've heard before. There are two versions of the CLEs, which are, just different ways to look at the same thing. One is just to ask that all these loops are, they're non-nested, or you can have another version where, you add more and, you have other nested loops inside. The way you construct the law of the nested configuration out of the law of the non-nested one is just to iterate, randomly, inside each of those loops you take an independent copy of another non-nested SLE and then CLE and then you continue. So let's focus just on those that are non-nested, so those ones here for the moment. Now, so the value of kappa comes from the fact that all these CLE loops are, each of these loops is locally like a SLE kappa loop, so it's a fractal curve, and you should bear in mind that what we're calling the CLE carpet is just this thing here that is surrounded by no loop, and that's a random fractal that is a cousin of the Sierpinski carpet. Right, so it hasn't any pinch point. It's sort of fairly fat, but still it's a fractal set, and we know lots of things about it. It's possible to compute its fractal dimension as a function of kappa, and things like that. So the way things work, and that's always one aspect. So there are different ways to construct them. Equivalence ways. Sort of one is using SLE exploration techniques, using this SLE exploration tree. This was the one proposed by Scott in his first paper on the topic. There's the thing with the construction with viewing these loops as outer boundary of clusters of independent Brownian loops. That's in our paper with Scott, which by the way has is somehow the unique one where you have, and maybe that's related, maybe Julien might tell me something about that. You know, there's this strange thing that, you know, when kappa increases from a third to 4, there's a natural way to couple all CLEs in such a way that these loops become larger. You know, they are sort of nested in some sense. So that's the only place where one is actually looking at structures where kappa vary. Anyway, so that's it. And one way, you know, the idea is that these loops, and I just want to remind you of this Markovian, I don't remember how we called it in the paper, it's got the Markovian conformal axioms, conformal restriction axiom. Which is the simple property that characterizes this random collection of loops. And the simple property is just the following, is that you sample this collection of loops and you cut something out. So this yellow piece that you bite out of the unit disk is a deterministic thing. Well, no, it could be random too, as long as it's independent from the CLE. And we're going to do that, you know, in a moment. When it's so you cut something out, and basically you can view each of these, you know, maybe I don't know, maybe if you are very interested in oil pockets or something like that, you can view these as, you know, oil reserves, right? And so you drill here, and then as soon as you find an oil reserve, you take everything out with a very nice pipeline, and then this is emptied as well, and then you look at, you know, the remaining piece of rock that you have in front of you, and the idea is that conditionally on this, so now you have discovered that, so, right? There's a cave there, you discover all the caves that you discovered. Now, condition on the thing that you have discovered, what is in front of you, the distribution that what is in front of you is still exactly a CLE, meaning a conformal, you know, the image, you take the unit disk, you map it onto the remaining domain conformally, and then the law of the collection of loops in the remaining domain have to be exactly in distribution the same as the conformal image of a CLE in the original problem. Right? And basically what we showed with Scott, now it dates back quite a bit, is that these CLEs are the unique, you know, random collection of loops that satisfy these axioms. Right? So it's a simple, you don't say it has to be SLE, no, you have this axiom, and then out comes, the only solution is to have a SCLE type loops, and for each kappa there's just one collection of them. Now this, you know, this axiom, you know, gives you very naturally, you know, if you think about, you know, peeling and all these things, it gives you very natural, you know, what you want to do as well, you want to define some sort of Markovian ways, Markovian algorithms that, you know, you are going to use to discover the CLE piece by piece, right? So you could say here, and that was sort of, you know, what we started, also part of how we proved these things, these axiomatic characterizations in the original paper. You know, you could start biting a little bit here, tiny bit, and then, well, maybe I discover a loop, or I don't, you know, then you suck up those small loops here, and then you bite out a little bit more, and then you know, maybe now here you find a big one, and now maybe you know, you have some sort of way to define how you're going to continue exploring the loops, you know, one after the other. And so it's clear that you could sort of start, you know, exploring a little bit, and then deciding, you know, you're going to decide how you continue exploring, how you continue to drill, depending on the caves that you have already found, right? So the idea is, you know, I start drilling here. So one thing you should have in mind is, you know, imagine that this is like a very nice Riemannian balloon that has the property that each time, you know, each time you start drilling, then you have a remaining thing, but the remaining thing immediately, you know, you take this piece out, but then it immediately fills the disk back again, so it's, you know, immediately mapped back conformally on the unit disk, and then you start drilling again on the boundary of the unit disk, and this thing, you know, so you have this sort of stationary picture that however, you know, you start drilling, what you have in front of you is just always a CLE. Okay? So these class of, you know, ways to continuously explore, drill into this, and discover the loops one after the other. If you use this idea that we always map back, and we are always drilling, starting from the boundary point, a given boundary point of the CLE using some microscopic, rule, is sort of called, Markovian natural, conformally invariant Markovian exploration properties. Okay. Okay, and that's also, that's just one way to understand what happens. Now, what appeared, so what I'm saying here is just, more or less is going to be sort of specific to those type of explorations here. I come back to probably to this story next tomorrow. I mean, on the other side, when the loops are not. So, one way to think about it is, you always try to drill, and suddenly, occasionally, you're going to discover a bubble, right? So, a boundary touching loop. And this boundary touching loop, because of the way SLE is defined, is encoded by an actually excursion of some Bessel process. So it's sort of very reminiscent, even at that stage, you immediately have this idea that, well, what you're looking at is something that is reminiscent of a, maybe a stable subordinator or stable process where the jumps correspond to the holes that you're discovering there, and that the size of the jumps maybe corresponds to something that has to do with the the length or the air or the height or whatever of a Bessel process excursion. Okay, so one result now I want to explain very briefly that we have sort of, which is in the, maybe I should, maybe I should just emphasize one thing, which is, before the CLE percolation paper, which is the following idea. So when you are using, when you're doing a continuous exploration, a discovery of the CLE loops one after the other, you're sort of drilling in sort of Markovian exploration ways, and occasionally you're finding, when you bump into the loop that is there, at the moment when you bump into it, what you are doing in effect is actually sitting on the boundary, because your balloon always takes back the whole space that you have in front of you, and what you are discovering here is one of these, like a CLE loop conditioned to touch the boundary at the boundary point where you are just actually drilling, say -1 here. So, which means that when you are exploring your CLE there, what you get is a Poisson point process of such boundary touching bubbles that you're discovering one after the other at the time, right? And they are IID just because of it's a Poisson point process just because of the Markovian axioms. Now, the question is, sort of once you have discovered that, this thing gets mapped back, and then you ask it, how do I continue drilling? I map this back conformally, it becomes yellow. Say I'm always targeting that point, in that direction, so this point is here, then I map back this, and then you have the choice to decide, now, I can use any conformal transformation that preserves this point, so I could, move things here a little bit, and I can decide, to either continue maybe drilling on this point or continue drilling on that point, or maybe somewhere in the middle, that means, I could continue drilling here or here or here. And as it turns out, the two natural options to continue drilling are going to be either here or there, just because what you want to do is, you want to trace this as a curve, so either you trace the loop in this way and then you continue like that, or you trace the loop in that way and then you continue there. It's nicer when you want to try to encode, continuous evolutions. And so, as it turns out, there's a natural way, to make sense of the following rule that consists of, as soon as I touch this, I continue exploring here. So the first reaction is to say, well, this will never work because, we are sort of, then then you're finding a new one here, and then you're finding a new one here. I mean, this is getting smaller and smaller. You never take off from the point -1. And the answer is, well, that's not true. It's exactly the same story as when you have a Brownian excursion and you concatenate them. No two excursions will be next to each other, and somehow that this process that you obtain by doing this will actually take off. And so what you are going to what you expect to do, what is going to happen is basically that you are going to always discover CLE loops, but actually you're sort of moving into the domain and discovering loops one after the other according to will be a bit like that with some sort of trunk, and I'll come back to a moment about that. So there are two things that are worth explaining and a bit perturbing, because some things have to do with two-dimensional randomness that occur here that are surprising if one thinks about one-dimensional randomness. The first one is that this entire process, Markovian, I'll come back to that description of that process in a moment. This process here, which is called an SLE kappa -6 process. For those of you who know about SLE, kappa smaller than 4, kappa -6, this guy is smaller than -2. So we are looking at something goes wrong with the Bessel dimensions of the Bessel processes. So one has to do, something has to be done. But the entire process is characterized uniquely by the Poisson point process of bubbles. Right? So if you know the ordered collection of bubbles that you're discovering in front of you, boundary touching bubbles, then you can reconstruct the process. However, and that's the outcome of one of the papers with Scott and Jason, is that if you condition on the CLE, so if I condition on that and I say I'm going to discover that using that algorithm, the outcome is going to be random, even though the CLE you're discovering is given. And I'm going to explain to you that in a moment. So now it's just a fact about the so-called CLE percolation. So that's one item in the CLE percolation paper with Scott and Jason, which is that the way to understand this Markovian exploration. So again, it is this exploration can be defined in a fairly axiomatic way. It's the unique way to drill into your domain that discovers, in a continuous way, that discovers loops one after the other, leaves, when you see a loop in front, then you leave it to your right, and you continue growing to the left of it, and in such a way that the growth, the growth is conformally invariant. And the CLE percolation can be interpreted as follows. So if you condition on the CLE kappa carpet, there's a natural way to decompose the carpet into something that you can interpret as doing critical percolation within the carpet, right? So within this very thin thing here, which is a fractal domain of dimensions smaller than 2, you can define something that would play the role of critical, percolation clusters that try to make their way in between the loops. Okay, so you condition on the loops, and then you have this thing that is this critical percolation that tries to, the water that tries to infiltrate within this fractal domain. And basically what we sort of explained, that there's a unique way to do that in some sort of conformal invariant way. Okay, and that the way to think about what one is doing here is basically to say that, we are following, imagine here. So here you have the collection of all these percolation clusters that are living in that are, touching the boundary here and that are living in the complement of the CLE. And of course, percolation clusters that live in a domain, their boundary will touch the CLE loops, right? So they are, they try to grow, and if they bounce into a CLE loop, they say, oh, well, it's a hole, we can't go there, but we bounce into there. So they are basically going to touch these objects here. So this exploration process that I described to you before, the way to understand it is basically going as follows. You are following the outer boundary of this percolation model inside the CLE, and each time you find a CLE loop, you attach it to your model. Okay? And so there are two remarks I want to make. The first one is that this exploration procedure, of course, once it bounces on the loop, it will bounce many times again on the loop. It can touch the boundary of the domain as well, because it's just it has no notion where the boundaries are until you hit them, and will touch the boundaries both on the right and both on the left. Okay. So as it turns out, the law. So what one can fully describe sort of the one can describe. Okay, I'm not going to write it down. You can describe basically the law of this percolation model inside the CLE carpet when you condition it on it, and you can say then the law of the CLE of the exploration process that I've described here conditionally on the CLE it describes can be obtained in this way. The other remark is that the quenched law, so now if you first sample the CLE, then you do the purple stuff, and then you remove the CLE, then you don't know anymore where the loops are, and you look at just the law of this purple structure, of this purple collection of clusters. Then it turns out that this is something one can describe very well. This is an SLE kappa prime type curve. For kappa prime equal to 16 over kappa. And that should surprise no one, because if you believe in the fact that the ON models have a scaling limit, conformal invariant scaling limit, and the FK model that is coupled, that FQ POTS model has a scaling limit, and the FK model that is coupled to the POTS model also has a scaling limit, then one can interpret the FK model as a critical percolation inside the POTS model cluster. So this is representing the scaling limit. Say, if you take a plus easing model with plus boundary condition, this carpet would be the scaling limit of the cluster of easing, of the plus cluster of easing that touches the boundary. And then these purple things would be basically the boundary touching FK clusters associated to it.
Benji?
Yeah?
That's also the only way for your thing to be consistent, because the boundary of the loops has dimension, correspond to kappa.
Yes, yeah. I mean, okay, there are many reasons for this to be consistent, but so for those of you who want to learn more about the CLE percolation stuff, there's a long paper. I think we like it, the three of us, very much, and we wish that people read it and like it too. Now, the point is that so of course here we see there are a couple of rules, arbitrary choices one made. One arbitrary choice was to say, well, I drill into my domain, and when I discover a loop, I leave it to the right instead of, which in a way you can view it as, when I discover a loop, I'm not going to trace it clockwise or anti-clockwise, because, that's going to tell you if you continue this way or that way. So a very natural thing to do as well would be to choose a parameter between 0 and 1, and each time you find a loop, you toss a coin to decide whether you go at clockwise around it or anti-clockwise around it. That would still be a conformally invariant, choice, obviously. And then basically for each choice, so this is usually the parameter we use is beta, which is between -1 and 1 for historical reasons. For each choice of beta, you basically know what's the probability when you bounce into a loop, whether you trace it this way or that way. And then there's a corresponding exploration process as well. And so the whole structure here gives you basically the joint distribution of the loops that you discover and what we usually call the trunk, which is basically the outermost boundary of this SLE kappa prime process that you get there. So let me just make a very brief remark. Right, so the way you should think about it now is I have a starting point on the left, -1. I have a target point 1 that I've chosen to start with. But I could also, as in Tim's case, when I need to choose, I can choose whether I go right or left. But And so the idea is, I'm discovering I have this trunk, which happens to be a non-simple curve, right? And here, on the side of the trunk, you have the CLE loops that you discover. They have some structure like that, right? So they are attached to the boundary, and they can touch the trunk to the right side of the trunk, right? And you can also have, structures like that where you have this loop here, and then here you can have another one that is squeezed in between the first time you hit the loop and the last time the trunk hits the loop, okay? And so the law of yellow given red is what we call a boundary conformal loop ensemble, because you can also sort of describe it in that way. Okay, and when you drill, right, when you do our conformal exploration process that we have there, basically at that time here you are, say you are sitting somewhere here, drilling here. When you discover a pocket, you discover it all at once. So that would correspond to a jump where you sort of suddenly discover a CLE loop. And maybe when you drill, maybe at some point, the red thing bounces into a loop that it has discovered before, or in which case it will disconnect this piece from the target point 1. It can also, bounce, say, on the left boundary, then it will disconnect this piece from the target point that you have on the right? So the trunk is a non-simple curve, and it can bounce, it could hit boundary, so it would, by growing a small piece of the trunk, suddenly you could disconnect, macroscopic pieces away from your target point. And say, when you do that, of course, when this happens, then you have to know, well, the target point is on the right, I continue drilling on this side, or the target point is on the left, and I continue exploring to the left. Okay. So this is this SLE kappa minus 6 process, which is basically you follow the trunk. So all this is results of the CLE pocket. You follow the trunk, and then as soon as you hit a yellow loop for the first time, you can decide to attach it, sort of, go around it anti-clockwise, and then once you did that, you continue there. So this is the SLE kappa minus 6 process, starting from -1 to 1, that you can alternatively describe by the Poisson point process of bubbles. Now, just a side remark is that this description shows you one little thing, which is that the law of this SLE kappa minus 6 is not reversible, because if you go from -1 to 1, when you have a picture, say, for instance, with these two nested things that are here, the one that goes from -1 to 1 will hit this one, trace this one first, and then this one after. But if you go do the same drilling coming from the other side, then you will hit this one first and this one after. So it's not the time reversal, the usual time reversal of the curve that you see. On the other hand, what you see is that the picture is time reversal. It's time reversible. So the trace of SLE kappa minus 6 and the collection of loops, the loop trunk decomposition, is time reversible. But then the order in which you are going to explore your stuff, depending if you go from -1 to 1 or from 1 to -1, is going to be sort of slightly messed up. So that's just a little side remark that, some of the non-trivial consequences you get out of that. Okay, I just want to emphasize another thing, which is the way things are set up. It was highly non-trivial to prove that actually, the law of this red trunk that is sitting behind the scene of when you drill is actually a continuous curve, and that's sort of part of the CLE percolation result. Okay. So that's one part of the story, which is just about CLE, right? We have the CLEs as this collection of loops with, that you can view as like pockets, and there's a natural strategy to discover them in a Markovian way, which is sort of drilling into in a conforming invariant way, drilling into your domain, leaving the loops always to the right, and continue drilling. Okay. Now, the other player in the statement are, of course, the quantum surfaces that you want to put on top of this story. So there are two quantum surfaces that are going to come into the game here. When did I start? 15? 20? So there are two types of quantum surfaces. So for kappa between 8/3 and 4, we are going to associate two type of, then we're going to do we are always going to take gamma equal square root of kappa, and there are two natural gamma quantum surfaces that we'll need here. So gamma quantum surfaces in the sense I said yesterday, which is basically in the Sheffield, Miller-Sheffield, Duplantier, Miller-Sheffield sense, which are these, random pieces of space equipped with a special area measure, which is conformal invariant. And this area measure comes out of, is locally inside any piece of, inside the domain or piece of the boundary. It looks like a, free boundary Gaussian free, coming out of the regularization procedure from a free boundary Gaussian free field. So I don't want to spend too much time, in the actual definition, but I just want to basically explain how it works. The first one is basically one special, if you use their terminology, is one special wedge, but because of the fact that it's actually a special one, it's very natural to call it sort of the quantum half-plane. And this one is basically, so I think for you guys it's the W equal 2 quantum wedge. So the idea is the following, is suppose you have, and that will allow me to say a few things more about these quantum surfaces. Suppose you have you're looking at the half plane. So the domain is going to be the half plane. And you start with a free boundary Gaussian free field in the upper half plane. Right? So then if you start with a free boundary Gaussian free field in the upper half plane, then you are getting, it sort of defines you some sort of quantum surface. But the one thing you want to do somehow is, as I told you, if you have that, then you can define, it's a usual problem. There's this usual slight, problem about, how do you define, and that's, in the way that they define it also first in the strip as the usual problem. If I give you this law as a process that goes from minus infinity, goes to plus infinity, and it's a Brownian motion with drift. Right? So, how are you going to describe this object? You have to somehow decide where to put the coordinate axis, because it's sort of defined. And depending on your choices, if you're not careful, then you can have some, size biased, measure in the end. So the way you want to do it is suppose you start with a free boundary Gaussian free field, and then you give yourself a very large, the idea is you want to see how does it look like in the neighborhood of something that you would call a typical point for when this point is chosen according to the boundary length. Right? So typically what you have is, imagine you have a free boundary Gaussian free field and you take it, so everything, now this as I'm saying is like, the very basics of the definition of these things that they've been working with for many years now, is, imagine that you have this boundary length measure defined here, and then you choose a special point according to the boundary length measure. Of course, the boundary length measure is going to be an infinite measure, so things are going to be a bit messy. So you choose a very large x, and then you look at the boundary length measure up to it's minus x here and it's x there. So the total boundary measure of this thing will be 2x, and then maybe you just choose one point at random in that interval according to this boundary measure, renormalized boundary measure. So you take a point, that is sampled here. Okay, and then you look at what you're seeing here. You let x goes to infinity, and you look at what's happening there. So then it's pretty clear that when you do that, This point, well, first of all, it will be a special point because it's, in the support of the boundary measure, which I told you is not it's not a smooth thing. It's going to be this boundary length is going to, select special points that are chosen according, coupled with a free field. And of course, everything is defined up to multiplicative constant. So there's some sort of, bias because this one will tend to have, the value of the field here somehow would tend to be higher there than its neighbors because it has been selected, right? So so somehow you would expect that the field, that is sort of locally prefers to be a maximum bit higher where the free field is higher than some others. And so basically when you apply this procedure, what you end up with is you have this special mark point, which is there. You have a free boundary Gaussian free field. And somehow to the free boundary Gaussian free field, the effect of this choosing this special point is going to, create a singularity where you add something like that to your free boundary Gaussian free field, where you decide that this is 0, you reshift so that this becomes 0, and then you add this singularity, this harmonic function that basically tells you that actually, measures the sort of bias that you did put into there. If you do that in that way, this is going to define your quantum surface in the way that I've described yesterday. And this quantum surface has a very nice property, which is that, if 0 is going to be a very special point here because it's going to be a point that is in the support of the boundary measure. But if you just, the way I set up things here, if you shift, if you choose a number, say 1, and you take the first point y here such that the boundary length between the two is 1, then seen from here, shift everything, you have the same measure on quantum quantum surfaces, right? So somehow what you see here is that this is not exactly a probability measure of quantum surfaces in the sense that the boundary length is infinite. So you have to make it a probability measure. Somehow you need to fix a special boundary point which you choose according to this boundary length measure, and then this measure on quantum half planes, which are marked quantum half planes with one boundary point here, is going to be invariant under the operation of shifting this special marked boundary point according to the boundary length. So the way you should think about it is that, say, if we map that conformally onto something like that, then you have this marked boundary point here that is the image of this one, which is a typical boundary point chosen according to the Lebesgue measure. But you have another very special point, which is the image of infinity, right? So here you have infinity. And what happens is that the boundary length of any piece here that doesn't contain infinity is going to be finite, but the boundary length of any neighborhood of the image of infinity is going to be infinite because it's just the image of this object, right? So of course for planar maps, it's like you take, it's the usual thing, you take something with an infinite boundary and then you try to take the scaling limit of the object that is defined with the infinite boundary. That's a quantum half plane. So I want just to emphasize that there are these usual problems when you have this structure which is defined and you want to find, you have the e to the gamma Gaussian free field, and somehow what you are trying to do here is define a way to have as few marked points somehow as possible, right? As canonical as possible, and the good way is somehow to use the measure itself to choose your marked point, which is what one is doing here by choosing this point 0 according to the boundary length measure somehow. That's somehow so for planar maps, people, right, you want to look at the scaling limit of a planar map with an infinite boundary with a typically chosen marked point. So you root, you choose some root point on the boundary, and then you look at what you see seen from that root point. That's basically what one is doing there. Because the length of the boundary, the limit of the number of points that you see on the boundary is supposed to go to something that has to do with the boundary length. That's our first friend, the quantum half plane. Now the second friend are the quantum disks that play a very important role in all the mating of trees and all the papers by Scott and Jason on the topic and Bertrand on the topic before. And somehow this is the natural way in which you can define a quantum surface that has, in a domain that has a finite boundary length. Right? So that would be the scaling limit of something that has to do with a planar map with a finite, certain number of points on the boundary. You let the points on the length of the boundary go to infinity, and then you try to find the limit of the global object, not just zooming in into this special point. So the gamma quantum disk. Okay, so maybe I'll just give you the alternative description that's going to come out, of the result I'm going to state. So I'm going to do the other way around. But the way you can think about it is take a CLE kappa loop. This CLE kappa loop lives in an entire, there's a whole plane GFF sitting there. So it lives in the whole plane. Another way to do it is take a tiny CLE loop in the unit disk, do a GFF there, so then you look at the trace of this GFF in the entire disk, the trace to this tiny CLE loop. So that's going to, of course, I told you things are defined up to constant and things, so there's the scaling invariance property that makes it possible to you cut this out, right, and then that's your piece of quantum surface. And so you just see the law of the whole plane GFF restricted to the inside of an independently chosen CLE loop, right? And that's some sort of a recipe that is going to turn out to be equivalent to the other definitions of quantum disks that you can, try to cook up by, limiting behaviors up there, right? So it's the structure that you see when you do that. So typically here, what happens is when you map this. Okay, I'm not going to.
So again, there is scaling variance, so you don't fix any point.
Okay, so now there's the thing which is exactly. So now the boundary length is going to be finite, right? Because the way we set up things locally, there are SLE curves all the way because these are SLE kappa loops. So if you go once around, it will be finite. But because the GFF has been chosen, up to an additive constant somehow, then the boundary length is also chosen. There's some sort of scaling property. So you have two ways to define it. Either you define the quantum disks conditioned to have boundary length L, or you define an infinite measure, so the natural measure mu, and the measure mu on disk is going to be, and as it turns out, there's one magic scaling factor, right, that is associated to, which is basically you're going to integrate the boundary length dl over L to the alpha plus 1, where alpha is 4 over kappa, times, the probability on quantum disks with boundary length L. Right, so there's a natural sort of scale invariant choice of your boundary length that you want to choose here. And you'll see why this is the natural way to proceed. Okay, so here there's a natural infinite measure somehow on things that you can decompose in choosing the Lebesgue measure here of the boundary length multiplied by this measure on half planes. And again, the half plane itself is also defined, the h is defined up to a multiplicative constant. So you should view this as a measure that tells you what is twice larger and twice smaller. And here you have this infinite measure on quantum disks. That is, you can view as unscrew it by saying, well, first you choose the boundary length according to this particular infinite measure, and then you choose somehow the object that you have inside. And of course, the quantum disk with length L is just exactly the same as the quantum disk with length 1, except that you have just multiplied everything by a certain factor. Okay, so these are our two friends. So now the statements are the following. So statement, so that's this CLE on Liouville quantum gravity papers with Scott and Jason that we've been talking and discussing about for 2 years, I think now, and discussing with various people. And I'm currently the slow bond in the thing, and I'm sort of I'm the reason why it doesn't come out, hasn't come out yet, because okay. So the statements is the following. So that's in sort of Miller. So let me just do the following. We consider a gamma quantum half plane, right? So it's this thing here. So again, it's defined, up to multiplicative constant, but then you can also integrate out this multiplicative constant. So the picture is going to be scale invariant, a quantum half plane. And so here 0 is, right, it's this idea where 0 is a boundary typical point. Okay. Now you consider a CLE kappa in the upper half plane that is independent from the gamma quantum half plane and its exploration. From 0 in the sense that I've described before, right? Sort of here. So what you have here is you're starting here. So you have this quantum surface that is sitting there, and independently of that, you have this collection of loops that you have here, which is just the image under a conformal map from the disk onto the upper half plane of a CLE. And you're discovering the loops one after the other with this loop trunk, decomposition like that. Okay, so seen from infinity in the exploration, seen from infinity. So there are 3 things that can happen. So one discovers loops. So let's call LT somehow. There's some time parameterization of the trunk. LT, T positive. So that would be the inside of the CLE loops that one discovers. Right? So this is a point process, right? So there's a collection LTI at special, countable number of loops that you're discovering, and you're discovering in a certain order. So this is this process that you have here. And of course, because you have, printed it on top of a Liouville quantum gravity independent one that you have defined here, these are going to be, you can equip with the trace of the original LQG surface, right? And so therefore, you have a Poisson point process of quantum surfaces that you're discovering along the way. Now one cuts off unexplored pieces, the trunk, unexplored pieces, right, to its right. Let's call this UTJ plus and UTJ minus to its left. Right, so the picture is just, you're exploring here. If I discover a loop here, this is going to be one of the L's. Then a bit later, maybe the trunk is bouncing again here and there, so you're cutting out this. That's That's a typical UT minus. Or maybe the trunk is, bouncing here, then you're cutting out this piece, that's going to be a UT plus. No, that's a minus 2. So if you go back here, no, that's a UT plus, sorry. That's a UT plus and that's a UT minus. Okay. And is that clear? And if I take any point x in the upper half plane, eventually it will either be inside a loop, it will be sort of disappear from infinity by the exploration, and eventually it will be in one of the LTIs or one of the UT pluses or one of the UT minuses. Right? So the theorem is if parameterized correctly, if the trunk is parameterized and the parameterization, it's not a big deal, it's just comes out of the result itself, then I have to be careful with here, then LTI, UTI, U plus TI and U minus TI are independent Poisson point processes of quantum disks. Right? So the stuff you're bouncing into in front of you is just IID. So the pieces of quantum surfaces that you cut out to the right, that you cut out to the left, all the loops, they're just, there's some sort of a stationary picture where, you're discovering things and they are actually IID.
Don't you need 2 points when you cut out from the left or right?
No. There are no marked points. That's the somehow the, I think. Okay, so let me. Okay, so let me sort of continue a bit more here by what I mean. So now the respective intensities can be chosen to be, they can chosen to be 1/2 of mu for u plus, 1/2 of mu for u minus. Okay, and now there's a magic constant here, right, which is this minus cos 4 pi over kappa times mu for L. Okay, so that means that what you're cutting out to the right or to the left, even though a priori the way you're discovering things is very non-symmetric, is actually the same. And what you're inserting here are the loops that you have in your middle, and they have a certain intensity. Now I want to make okay, maybe I should go immediately to the next statement. Okay, I'll write down the other statement for the quantum disks. Right, so this tells you somehow that if you view it in the other way, that you have your processes of quantum disks, right, that you're using to discovering along the way, and that it suggests that if I given the 3 processes of quantum disks, then you're just doing some sort of patchwork by gluing them together, one after in the way they arrive, to the right, to the left, and so on, depending on whether it's a U plus or U minus or an L. And then what you glue together, in the IID pieces, what you get is exactly the is the CLE on the Liouville quantum gravity surface. Okay, so that when you put them one on top of each other, even though at beginning they are independent, okay, then there's a way to, when you explore them in the Markovian way, that suddenly you can explore them together in such a way that you get some IID and a nice Poisson point plus. Now, a little remark, of course, is that this, when kappa is between 8/3 And 4, this moves between 0 and 1, which corresponds kappa equals a third. This is 0, there are no loops. And 1 kappa is equal to 4, then this minus cos pi over kappa is going to be minus 1. And that corresponds to the fact that, the volume of what is remaining, what you still have to explore, has not to blow up. So you need at least, you need to cut out more stuff than stuff you put in by, by adding loops. And so this has to be small, cannot be larger than 1, otherwise you have an infinite volume surface. Okay, so now the quantum exploration of a quantum disk. So now this idea here is, which is very important somehow, because here what we do is we explore our CLE, we find loops, but then we have all the pieces that fall off to the right or to the left, and these pieces are quantum disks. And what we would like to do is be able to continue exploring there to understand what, the whole thing, discover the whole picture, to have the whole tree. So then you need to learn how to explore a quantum disk. And the way one explores a quantum disk is basically saying, it's just basically using an H transform of this piece here. So the idea is, I'm going to explain it tomorrow, but the basic idea is going to be that if you start from a okay, maybe I'm going to do that tomorrow. Don't want to be over time every day. Those of you, or maybe I'm not sure how many of you followed my courses when I was giving courses back in Orsay, where the time limit was not enforced like in Switzerland. You used to go over time very, very badly. Do you want to have a lunch break before we continue or not? But now in Switzerland, it's very tough for me to finish on time. So now as soon as I'm abroad, I try to steal time. But I'm not going to explain you, the exploration of quantum. I'm going to do it tomorrow, but just for you to understand what one is doing. The idea is that we are sitting somehow on the boundary at a given time. You are sitting on the boundary of a quantum surface, right? So you have explored this, right? Which is this past stuff that you have explored from the loops plus the trunk. And this is the boundary of what remains to be explored, and this is somehow a boundary typical point for the Liouville quantum gravity surface that is in front of you. Now, there are two things, the whole evolution, and that's sort of the basic stuff in the mating of trees as well. The whole evolution will be governed by actually the fact that you explore a tiny bit here. Okay? So if you iterate the exploration of tiny bits like that in a natural way, if there's no CLE on that, then you end up with something which looks like tracing an SLE kappa prime. Now, if here what you explore is what was remaining in front of you because of the CLE exploration property, is still some quantum surface on top of which there are the loops that remain to be discovered. Now, there are two things that can happen and that are governing the whole evolution when you are doing that. The first thing is you might be here and discover a little blue thing here, and it so happens that the boundary of the domain that you remain to explore comes back into this very small neighborhood, right? So when you do this little, you eat up, and then you say, oh, well, first you think, oh, I'm very happy, I found an actual, pocket, but actually you realize, oh, it's not a pocket, I just cut out something here, okay? And this will happen somehow because you are always exploring a certain quantum surface that is sort of stationary. This is going to happen at a Poissonian number of little exploration pieces. And the other thing that can happen is that you are sitting here, you expose this little bit, and you find a loop. And then you have to jump. Now, this thing can happen either to the right or to the left, so then what falls off and is going to be a quantum disk, because that's sort of this idea of Scott and Jason that corresponds to pinching off, or to Scott probably originally, that you pinch off a finite piece out of a half plane. And the thing is, of course, what is this more likely than that? the answer is, well, no, because both things have to do with the probability that an SLE curves come close to the boundary. Again, they are both governed by the same exponent, so there's an even sort of competition between the two things, which explains why you have the stuff that correspond to falling off, you have the loops that you encounter, and of course the big magic thing is that everything is just stationary IID, that you are discovering IID things in front of you. So of course there are many things I didn't say. So one just little remark is that well, maybe I'm going to make those comments to compare this to the mating of trees and sort of what the essential difference is. Probably going to explain that more, discuss that tomorrow. I don't want to eat up more of your lunch time. But somehow what you see here is that with those, these things correspond to jumps, okay, and that you are sort of looking at, you are mating excursions of stable processes rather than of correlated random walks. That's sort of somehow what is going on there. Okay, so thank you.
Thanks a lot. Any questions? Everybody's hungry. Okay, so let's thank Wendelin again. Let's have lunch.